In the previous segment, we investigated standing waves on a string. Another really interesting example of standing waves is standing sound waves in a pipe. And there's a lot of examples of this. Any type of woodwind instrument or a brass instrument creates the notes that it does by creating a standing sound wave in a pipe or a tube. Other examples include a bottle. I can create a standing sound wave in here. Look. I can even create a couple of different modes. Here's one mode. Here's another. Very loud. Okay. I can create a standing sound wave in this copper pipe. Lovely. Okay. That's what we're talking about. So we've seen the pictures for the standing wave on a string. And a standing sound wave in a pipe or a tube is very similar. And we see that the math is almost identical here. And we can either have a pipe that is open at both ends or a pipe that is closed at both ends. The open pipes are pretty easy to visualize. A flute is actually a great example of a pipe that is essentially open at different ends. In the segment on standing waves on a string, we saw these patterns here, right? The m equals 1 mode, the m equals 2 mode, and the m equals 3 mode. Notice that the patterns here look almost exactly the same. But for the standing wave on a string, it was really easy to see what those pictures represented. They represented the displacement of the string from equilibrium. Well, what do these blue lines here represent? Well, recall that a sound wave is variations in pressure. It's variations in pressure from slightly above ambient room pressure to slightly below the room pressure, whatever the pressure is in the room. That's what a sound wave is. And in a traveling wave, those pockets of high and low pressure, they propagate throughout the room, or in this case, through the room towards the microphone, which picks them up and turns it into something that you can hear. Well, what are we looking at here then? In a standing sound wave, those pockets of high and low pressure don't move. We have antinodes, like right here in the middle, where the pressure is varying from above atmospheric pressure to below, above to below, above to below. And we have nodes represented at the two ends of this pipe where the pressure does not vary at all. So what the blue line is actually indicating is how is the pressure varying compared to room pressure. Notice that just like when we dealt with fluids, any place where the pipe is open to the air, it's atmospheric pressure. And so we always get a node at a point where the pipe is open to the air. A flute or a saxophone creates different notes in that way. Any place where you have an open hole in your flute is a node. It is a pressure node. That point is always equal to atmospheric pressure, and so it limits the standing waves that can occur within that pipe. Notice here we have the m equals 1. Again, it is the longest possible wavelength. The m equals 2 example, which is the second longest wavelength, and the m equals 3, the third longest wavelength that will fit in the pipe. Now, we could have a pipe that was closed at both ends. That's a little bit harder to visualize, but there's no reason why we cannot create a standing wave in a pipe that's closed at both ends. Notice here that since it's closed at both ends, we end up with an antinode at each end and a node in the middle. M equals 1, M equals 2, M equals 3. In the previous segment, I suggested it's probably not best to memorize a rule, such as the mode number is how many antinodes there are, or the mode number is how many nodes there are, because it depends on what I'm talking about. If I'm talking about an open system, then the mode number is the number of antinodes. But if I'm looking at a closed system, the mode number is the number of nodes. And we'll see that I can look at an open closed system, which is even more complicated. Okay, so an open system is like a flute. Notice that the math for this looks exactly like the math we had for the wave on a string. It's exactly the same. Here we see the wavelengths as a function of m. Right? Here we're looking at half a wavelength. Here we're looking at one full wavelength. And here we're looking at 1.5 wavelengths. It's a little bit harder to see here, but it's the same thing here. Here we're looking at half a wavelength, one complete wavelength, and 1 1/2 wavelengths. Again, the math there is exactly the same as the math for the wave on the string. Now, there's no reason why we can't have a open-closed system. A clarinet is a good example of an open-closed system. Again, notice that this rule breaks down because now we have equal numbers of modes and antinodes. In the previous examples, we always had different numbers of modes and antinodes. Notice in this system, the number of modes is equal to the number of antinodes. And our math is just a little bit different too. One thing that we can always count on, though, is that any place where it's open to the air, that is at atmospheric pressure, and that is a node. Any place where the end is closed, that is a antinode. Now do be a little bit careful. There's a number of ways to describe sound waves. So we've been talking about sound waves as pockets of high and low pressure which propagate through the air. And that's the description we're using here, and it's completely correct. We can also visualize, as we've just demonstrated in a previous chapter, that as those pockets of high and low pressure move, the particles in the air move back and forth just a little bit. And so we can plot the pressure, as I've done and as your textbook does, or we could plot the displacement. Be careful. Those two waves are perfectly out of phase with each other. So if you go hunting for information on this on the internet, just be sure you are looking at the pressure wave descriptions and not the displacement wave descriptions. In this class, I will only talk about the pressure wave description. Again, notice the math is a little bit different. Here's a tricky one. The mode numbers here, they increase only by odds, right? And so do notice that we'll call this the m equals 1, the m equals 3, and the m equals 5. Again, our rule breaks down if we try and memorize how many nodes go with how many, with the m value or something like that, right? We'd have to memorize 3 different rules, one for every different situation. However, notice that we're just fitting the longest wavelengths we can in here. Here's the longest wavelength that fits according to our rules. A node at one end and an antinode at another end. This is the next longest wavelength that fits. And this is the next longest wavelength that fits. And then we just have to remember that for open-closed systems, we only use the odd. So here we have this copper pipe. When I put my mouth over the end, this end becomes closed and this end becomes open. So this is a system that's well modeled as an open-closed system. And I can set up different standing waves in this system. I'll give it my best. I'm not a brass player, but I'll give it my best here. Did my music touch you? I doubt it. The point I'm really trying to demonstrate here is that I can only create certain notes in here. I can't just create any old note I want, because the only notes that are going to be audible here are wavelengths that fit in this tube. And by fit, I mean obey the rules of an open-closed pipe. And so I can't just play any frequency I want. I can only play frequencies that correspond to standing sound waves that exist within this pipe. Let me show you an example of somebody doing this who actually knows what they're doing. This is a bugler, a military bugler, and a bugle is different than a trumpet in that it has no keys. So when you're playing a bugle, you're adjusting your lips, how your lips are vibrating, in order to create the different notes. You have a limited number of notes that you can play on a bugle, because there's no way to change the length of the pipe. That's what the buttons on a trumpet do, is they change the effective length of the pipe. And so on a bugle, you can't do that. So you can only play notes that correspond to these frequencies. Fortunately, there are some very nice songs that only contain notes corresponding with those frequencies. Let's check one of them out. Taps is another famous song that one can play without any buttons. So if I was more proficient at it, I actually could play that song on my brass pipe. Not today. Let's do a quick example. A child has an ear canal that is 1.3 centimeters long. At what sound frequencies in the audible range will the child have increased hearing sensitivity? Well, what does this have to do with standing sound waves? Just like an instrument will only create these notes that fit within that tube according to the rules of the tube, so too, these sound waves will resonate in our ears if they fit within our ears. And so we actually don't perceive all notes equally. We perceive notes as louder if they resonate in our ears. In other words, if their standing waves can be created within our ears. All right, so what this is really asking is what frequencies in the audible range create standing sound waves in our ears? This child's ears, I should say. Well, let's see. Should we model this as open, open, or open, closed? Well, on the outside end of my ear, there's a hole. So it's certainly open something. And on the other side is actually a membrane called the eardrum, which closes it off. So we should model this as an open-closed system. So what does that math look like? Well, that's what we have here. So let's go ahead and write this down. It's asking for frequencies. Okay, so this is our equation we're going to use. And we're going to remember to only use the odd m's because it is an open-closed system. We're looking for the audible range. Recall that humans can hear from about 20 hertz to about 20,000 hertz. This is a child with fresh ears that's never been to a rock concert. Okay, so let's go ahead and just see what we get. Let's see what F1 is. F1 equals 1 times, I've told you that if I don't tell you otherwise, use 343 meters per second for the speed of sound. Divided by 4 times, the length of this child's ear is 1.3 centimeters. Let's run our calculator and see what we get. So I ran my calculator and I got 6,600 hertz. 6,600 hertz. So that is in the audible range. We can also use this equation here, that F sub 3 is equal to 3F1. Well, what do we get if I run my calculator on that? Well, I just multiply this by 3, and I get, 19,800. So there you go. If I was to look for F equals 5, I get 33,000 hertz, well out of the audible range for humans. This right here, I bet most of you could not hear that. My hearing drops off above about 16,000 hertz.